So why do we need a new alkene synthesis method? Why would the Wittig be helpful in some cases compared to other ways that we've synthesized alkenes? Well, this might be a time for you to take a moment and think, well, how the heck do we synthesize alkenes? Because it's something that you should have up there. And essentially the previous alkene methods that we've known about are just elimination reactions. So we'll write that right here, elimination reactions. That's how we've synthesized alkenes in the past. If we wanted to do synthesis of this alkene from this oxygen, how might we do that? What do we have to add to the molecule? We have to add a carbon here. We have a CH2 here. And how can we add a carbon adjacent to the carbonyl carbon? And the method that we would know to do that is our organometallic reagents. So essentially, if this was a synthesis question, the first reaction you'd want to put in there with our previous alkene synthesis methods was CH3 MgBr, so a methyl Grignard reaction. We'll add our THF solvent, our polar aprotic solvent, and then 2, we're going to protonate that, so we need to do our acid quench, so the H plus being added. So that would add the Grignard there. We'd have the O minus that would then protonate once we added our acid. So we would have, as a product of that first reaction, an alcohol, and our CH3 has now been added there. Well, how do we get from the alcohol to the C double bond CH? Well, that's a dehydration reaction. A dehydration reaction is a type of elimination reaction. How did we do that? That is a chapter 9 last semester type thing. But essentially, we added sulfuric acid. That protonated that alcohol, made it a really good leaving group. And to kind of force the molecule off, there's greater entropy in the products because we go from one molecule to 2 molecules. We added a lot of heat. So you'd essentially reflux the molecule in sulfuric acid to make the elimination occur. Again, how did that happen? We formed OH2 plus, that formed by the oxygen grabbing a proton from the sulfuric acid, and then the elimination that we were wanting to happen would come from sulfuric acid's conjugate base, so we'll just write HSO4 minus, pulling off that proton there. But what's the problem here? That's what we want to happen. Is any side reaction going to happen? What's another product that could form here? So you pause the video, you're thinking about that, you wrote the other product on there. Yeah, so the sulfuric acid could, the anion, so that could pull off that proton, but there's no reason why it also wouldn't just pull off that proton too. It's also a beta hydrogen. It can do that just as easily. And actually, this would be a 2-step, this would be an E1 type reaction, so let's draw that in 2 steps. So essentially, that guy is going to leave. That's going to generate our carbocation intermediate. And then that HSO4 minus can pull that off to form that if we grabbed this proton. But the proton that I've indicated would actually make that product. So we're going to form a mixture of alkenes. What's the more favorable alkene? Thinking about that for a minute. You got it. Yep, you answered. This is a di-substituted alkene. We only have 2 carbons coming off of the carbons of the alkene, whereas this is a tri-substituted alkene. So this would actually be the major product. So why is the Wittig reaction helpful? Well, in some cases, our old alkene methods fail to make that desired product as the major product. This is the major product, this is the minor product. So if we want to synthesize this in high yield, the only option is that Wittig reaction. So that shows the utility of that Wittig.